If somebody could please check how it goes out to make sure that the pictures are in a more or less right location. It's gonna take few seconds. So the live is always say 10 to 15 seconds ahead of the streaming. So soon it's supposed to be available, and I figured I can even see that by myself. Let me see. I don't know how is that. Oh yeah, I see that it goes quite alright. Goes quite alright. I don't know how is my voice, but I mean the voice that goes outside, that's a little bit unclear. But other than that, it seems to be okay. So, guys, may I have your attention? So let's move on to lecture number 7. So this is the lecture. And what it means is the lecture prior to midterm exam. And we're all living because of the midterm exam. So it's something that is very important you to follow today. So what will be the content of today? Well, today I'm gonna first explain you one more example, how we can construct the equation of motion. We're gonna take a look at the numerical example that I'm gonna run with MATLAB. And then we're gonna shortly discuss about something that is entitled as a constraint stabilization. That will be a short topic. There's only a few slides to explain that to you. And then we're gonna move on to real content of today, and that's summary. And in summary, each one of the topics that I'm expecting you to know in midterm exam are rated. So they are rated with a different number of stars. So if you can see the subject matter where there's only say 2 stars and you're in a hurry, this is what I recommend you to skip. Don't read it. Don't put much attention to that. But if you, on the other hand, if you see the subject matter which is rated as a 5-star, that means that that's definitely something you must master when you get into midterm exam. So that's what we're gonna look today. And I heard from some of the students that there are some things that are a bit unclear. So we can discuss those unclear matters as well today. But mainly it's about summary and how to prepare yourself to midterm exam. How it sounds? Sounds all right. Good. What was that? You still don't hear you, so. Okay, so it's too much light. Okay. How is this? Yeah, I want to put more, lights off because you're gonna fall asleep if it's gonna be completely dark. So that's clear enough. My slides are clear enough. Good. Okay. So let's going on. So let's first summarize what we discussed last week. So we get started last week by creating the equation of motion, and everything started from the system that was not constrained. System where there were no constraint that combines the generalized coordinates together, but the system that the bodies can move however they want. So there were no coupling between the bodies. And if there were no coupling between the bodies, then you can simply create the equation of motion by setting virtual work done by inertial forces to be equal than the virtual work done by externally applied forces. But very, very important to understand that that's held only in that particular circumstances where there is no constraints. If you have constraints, meaning that there is a constraint that limits the motion possibilities with neighboring bodies, then you cannot set this equation that is shown up here to be equal to 0. Now let's see how is my writing today. So yeah, look, so it's automated, so it works fine. So this equation you cannot set to be equal to 0 if you have a system with constraint. How is that? That's simply because your virtual displacement that is mentioned here, it is imposed to all the generalized coordinates. And what you're going to do when you do so is that you will violate against the constraint. So the reason that this equation cannot be set to be equal to 0 is the fact that the constraints are not accounted yet. So the constraints are missing here. And now generally speaking, we have two different ways to account the constraints. And we learned last week the one way that was based on augmented formulation. And augmented formulation means that we are adding the constraints to original equation with help of Lagrange multipliers. So that's one way to do it. There is an alternative way, which is simply substituting the constraint inside of the original equation of motion, and that's what we're going to learn right after the midterm exam. And then, by the way, that's when we're going to leave the whole multi-body system dynamics. So that will be the last thing to discuss. So the system or the method based on substitution will be called coordinate partitioning. So we're going to divide our coordinates to two different categories, and that helps us to express this virtual displacement such the way that it is kinematically admissible, kinematically possible. But today we're going to look at the method where we're adding the constraint with help of Lagrange multipliers and how it actually went. It went such the way that we're adding them with Lagrange multipliers and Jacobian matrix, and that a method that is based or is called as augmented formulation. Now, how it goes, how it actually went in detail, it went such the way that, the previous equation, there was something added to it, and that was that Jacobian matrix multiplied by Lagrange multipliers. What is the physical interpretation of that additional component that we added to equation of motion? Well, this is something that is very important to memorize in order to score high from the midterm exam. The Lagrange multiplier, this one here, tells what's the amount of reaction forces that are applying in your system due to the constraints. So it's a reaction forces due to the constraints. So if you want to make a note out of the lectures, this is the place to do so, because this is something that, don't make a note, but put it in your head. Memorize it what it is. Remember, by the definition, the Lagrange multipliers are price you have to pay because of the constraints. So what it means in mechanisms, it means that those are the reaction forces due to the constraints, due to the joints. Okay, then the other component that was added here is a Jacobian matrix that is actually telling you where those forces are applying in your system. So where is their location? And that's defined by Jacobian matrix. So altogether, there are reaction forces, their location, and their magnitude. That's what they are. So now, once we have this equation here, we have unknowns that are acceleration of generalized coordinates and Lagrange multipliers. So obviously we have not enough information to solve this equation. So we need to get additional amount of information, and that we can get by adding here constraint equation. So now we have this one here that is put it in a writing here, and then constraint equations. So those together are called as a set of differential algebraic equations, which you may be able to solve already. But we did one more step to make it more solvable, to make it them numerically easier to deal with. And the one more step we did was that we converted this set of differential algebraic equation to be ordinary differential equation. Ordinary differential equation. And now comes something that you need to put it in your mind as well. The vector of unknowns is this vector. This is where your unknowns are located at. Now when you look at what are the unknowns, those are acceleration of generalized coordinates and Lagrange multipliers. So you have two sets of unknowns. One is telling you the configuration, because that's exactly what those generalized coordinates are doing for you. So they are telling you the configuration of the system, and then we have one additional component that you have to solve, and that's Lagrange multipliers. Reaction forces due to the constraints. So these two sets are something that you must solve when you're solving the responses of your dynamic system. So that's how it goes. Now, here's a summary. So this is how it looks. If thinking about, again, about midterm exam, it could be possible that I'm asking like, okay, so what is this particular component? What is that component and what is its physical interpretation? Well, that's a quadratic velocity vector. The quadratic velocity vector accounts the centrifugal forces due to the rotation. This could be the level of knowledge you must master each one of these components. Or another example could be, what is this? Mass matrix. And the mass matrix for one body in planar case consists of 3 by 3 matrix, and those 3 by 3 matrix components are associated to 3 tenuized coordinates, and so on and so forth. Then this is an acceleration of tenuized coordinates. This is Lagrange multipliers and so on. So that kind of level of knowledge I'm expecting you to have whenever you get into your midterm exam. But now, is it clear what is a vector of unknowns? What are the unknowns in this method? Clear? By the way, now the newcomers, they don't know that we have the way to communicate. And the communication way is this, meaning that, yes, I have a can-do attitude. I know what is this question, and this means that I have no idea. This means that when exactly I can go back home, and I'm confused. So what it is it, when I'm asking what is a vector of unknowns in this method, do you know what it is? So it is, again, acceleration and Lagrange multipliers. That's what it is. Clear? Okay, so let's get into in-class quiz, which is this one. In augmented formulation, the unknowns are. And augmented formulation, again, is a method that I'm just explaining to you. So it's a method based on Lagrange multipliers. And now, hold on, I need to put my Socrative on. So, now the big question today, is it going to be, you know what, 100%? It will. Because today may be today. Let me see, Socrative, teacher locking. Okay, I'm gonna launch this one. Hold on, it should be available momentarily. So it's available right now. So we have, what it is, 70, 80 students. And the answers are coming. So now the options, let me get back to this one. So in augmented formulation, the unknowns are acceleration of tenuized coordinates, Lagrange multipliers, that's option number B. C is tenuized forces, and then the D is acceleration of tenuized coordinates and Lagrange multipliers. Only one is correct, but which one? Which one is correct? Let's get back to here. That would be, by the way, awesome to score 100% today, because then, you know what's gonna happen if we're gonna do that? You all come here and we're gonna make a big, selfie, group hug, and then selfie when we're doing this group hug. That would be outstanding. And then I'm gonna send that picture to rector and say, look at this. I'm a teacher of the year. So, but we'll see. Let's see. First thing we need to do is that we have to score 100%. And that's a challenge. That is a challenge, because out of these 4 options, only one is correct. But which one is correct? 90, okay, so we have actually record crowd today. So it's a 95 students today. And there is no way to make a double lockings, as you're forced to use your student ID number when you log into the system. We're gonna get more than 100 students today. We'll see. We'll see. Then I still thinking, oh, there is more locking in. No, those last lock-ins are something that makes me a bit scared, because those are the ones that are surfing around in the internet, and then they hear this thing that, okay, in-class quiz, and then they look the options and they have no idea what it is the correct one. So we'll see. So we're missing few. Good. Well, look at this. So it seems that this is going to be a record number. We're going to get 100. Not 5, I'm still thinking. So let me put this a little bit aside, and then I'm gonna go back to this in, okay, 4 students are still thinking. You guys are done. And you know what is the correct answer? You sure about that? Absolutely sure about that. 100. Look at that. Look at 100 students, 100, success rate. That would be really something. That would be really, really something. That would be my dream day. But let's not jump ahead. Let's first see how is the scoring. 4 students are still thinking. I'm a bit scared, like what makes them to think this long. But we'll see. We'll get back to that in a moment. Now, while they're thinking, let me show you something. This came from one of you guys. You sent me an email asking, like, what was the deal with this lecture that was delivered a few weeks back? So this was actually lecture number 5. And in lecture number 5, everything seems to be correct except the last explanation that was provided in the slide. It was mentioned that the moment becomes 0 when the angle is 45 degrees or 315 degrees. The one of these numbers are not correct. And the one number that is not correct is this one, 45 degrees, because obviously it's supposed to be 135 degrees. You may be a little bit confused, like, really? How it goes? Well, it goes such the way that you need to take a close look about the body reference coordinate system that is located here. This is x-axis. And I'm measuring the rotation of x-axis like this, starting from here, of course. This is equal than 315 degrees. And the way that it is showing, when it is pointing downwards like this, that would be equal than 135 degrees. So the number 45 was incorrect in my slide. So thank you for correcting that. So, for your information. And I'm sure you figured that out already a while ago, but you were just so convinced that it is incorrect that you didn't even let me know that, I guess. Okay, let's get back to this. Is it moment of truth? 3 is still thinking. Okay, so what if I close this in 5, 4, within 2 seconds, 1 is still thinking. That could be that critical thing. So within a second. Now, how is your case regarding the success rate? 99, 75, 75, because it's so damn difficult to know that it is 98. Let me put this in such a way that is more readable. 93. So that's a good news. So it's a good news. So it's a record high, considering that we have this many students logging in the system. So in that perspective, we never got that many correct answers. So now, to give you the right answer, let's get back to here, this equation. This vector is the one that we're gonna solve. How we gonna solve that vector? We're gonna go ahead and solve it by taking this one here, which is called system matrix, and we're gonna invert it and put it in the right hand side of the equation. So once doing it, then becomes clear that what we're gonna solve is acceleration of generalized coordinates and Lagrange multipliers. So we have 2 sets of unknowns, not 1 but 2. So the correct answer was, again here, when I'm moving down, D. So the D is the correct one. Yes, sir.
There was only one that answer that was like generous forces, but all the others should be accepted.
Well, they could be. That's a good argument. That is a good argument. Except that, usually they are solved as a coupled system. But you can argue and say that, it's still possible to solve just an acceleration. And yes, you can do it, just an acceleration. It's possible to do it. But this system is designed to be solved as such that two sets of unknowns are solved. So only the one that is completely correct is C. You're right about that. So it's maybe, if you could confuse that you select three options, correct? Not you, of course, but your fellow student. That was the one that made that mistake. So it's kind of like, understandable. So what do you say? Should I give credits to those ones that are also selecting A and B? Yes. Others, what are you saying? No? No. Yes? What? We don't convert. So what is a final conclusion?
Wasn't all unknowns, but only unknowns.
Unknowns. That's a good case. That is a good case. You want to make it stronger than that? Because can you really? Yeah, well, that's. We'll consider. Okay. So later today there will be another in-class quiz, which I really have a high hope. I'm really emphasizing something soon, and when I'm doing that, please listen to me. Put your, your computer aside or whatever you are doing. Put that in aside and focus on me. Because I'm really hoping that today we're gonna score, yes, 100%. We'll see. But you have a good argument. Let me go back and see here, but still 2% generalized forces. That's absolutely incorrect. It's same than rotation of a particle. Equally wrong. All right, so let's move on. So we were here, and now what I'm gonna do next is that I'm going to solve you another example based on this Alchemy formulation. Another example which now consists of two moving bodies. So two moving bodies, and that's what we looked shortly last week too. So how many generalized coordinates I have in this system? That's 6. That's 6 because I have two moving bodies, and each one of the bodies have to have 3 generalized coordinates. How many constraint equations? 5. 5, because here I have revolute joint that needs 2 constraint equations, and then I have here another revolute joint here, an additional 2 constraint equations. That's now a total of 4, and then one more that is located here, and that's a primitive joint that is only constraining the motion along the global y direction. So this motion is not possible. So that's 5th. So a total of 5 constraint equations. So what's the number of unknowns in this case? All the unknowns. All the unknowns. So it's 6 plus 5, that's 11 unknowns. Because 6 generalized coordinates, 5 constraint equations. Each one of the constraint equations must have a corresponding Lagrange multiplier. So that's where the number is coming from. Okay, we are not gonna do that, but we're gonna skip it. And then we're gonna look at all the steps. So we have, again, 6 steps to take. 6 steps. How is the first step? So let's create the mass matrix for 2 bodies. And now I'm not gonna do this in a hard way. So I'm not gonna use these volume integrals to get into mass moment of inertia, but instead I'm gonna take a look at the pre-calculated tables. And if you don't find these pre-calculated tables, I can give you some in model database. Now, the first important observation is this. The body reference coordinate system for both bodies are located in the center of the mass. Because, here in this beam-like body, this is where the body reference coordinate system is located at. Let me change the color. Here, where the body reference coordinate system is located at. So that's a good news. It's a good news because it's going to give us a diagonal representation of mass matrix, and it also makes it clear that our quadratic velocity vector will be equal to 0. So it simplifies the equation of motion in 2 ways: mass matrix and quadratic velocity vector. So now let's get started from the mass matrix. So it simply can be written as it is shown here. So this is a mass matrix for the first body. And now look what I have. I have here diagonal representation because of the fact that, again, the body reference coordinate system is located in the center of the mass. First two diagonal components are mass of the body because those are associated to generalized coordinates Rx and Ry, which is translational motion. Third, it is associated to rotational motion, and it is a mass moment of inertia. That's the one that I got from pre-calculated tables. By the way, this is the one that we got last week already. It says mass multiplied by length power 2 divided by 12. Okay, clear. The same thing for the second body, because that too is a beam-like body, and in that body too, the body reference coordinate system is located in the center of the mass, so there is no difference. And now comes the assembly part. So I'm taking my first body, put my mass matrix here, with no overlapping. And this is different than in a finite element method, where there is an overlapping. So now I'm going to put my mass matrix associated to second body here, and now you can see that this is 6 by 6 matrix. Why is that? Because I have 6 generalized coordinates. So each one of the columns and rows are associated to my generalized coordinates. Make sense? Okay. Then Jacobian matrix may be the most painful step to take, but doable still. Now, let's first look how is that I can create the rotation revolute that is located in a point A. So it's a, I don't know what is this point. So it's a body A and this particular point. And now look, there is a high temptation to not to travel anywhere, because global coordinate system is located here, exactly where the body, this revolute joint is located too. That doesn't matter. We still have to first move the body reference coordinate system and then back. We always have to do that. No shortcut is allowed. Even though that there is an obvious shortcut, never allowed. Always first the body reference coordinate system here, and then with help of vector u-bar, we're gonna go back. So first we're traveling the body reference coordinate system. We are counting its orientation, and now with help of the vector u-bar, we're traveling back. What does this equation have to be equal to? Well, it has to be equal to 0, 0, because that's where the point is globally located at. So that's why this vector must be having components 0, 0. You got it? A vector u-bar, that have to be, because look at where the x-axis of the global coordinate system is pointing at. So it's pointing opposite direction where we have to travel. So that's why this one here is L divided by 2 minus sign, because we're traveling the minus direction. Okay, so that's going to give me 2 constraint equation, first and second. Then we're going to follow the same procedure to express the revolute joint that is located in this point here. And the point is called P, very small font, but it's P. Okay, so we're gonna do this such that we're gonna first go to this place, this point, by using this body reference coordinate system. We're gonna redo the whole thing, but using the body reference coordinate system B. And once we put in those 2 equations to be equal, that means that this point have to be common no matter what. And that can be expressed mathematically like it is on here. So first translation, then orientation with the u-bar, and the same with respect to body B. And once I put in all these components, the left-hand side of the equation, and setting that to be equal to 0, that's going to be my 3rd and 4th constraint equations. Clear? So it's like soft stuff, not difficult at all. And it's not difficult at all because, you know, the one equation that you must memorize is this. The equation that we use to express the kinematic. And then you just keep on reusing that equation over and over and over again. But always you must use that equation. No other equations are possible when you define the kinematics. Constraints are part of the kinematics. Okay, then this point here, which is a point Q, How that goes? Well, it goes similar way that first I'm traveling here to body reference coordinate system, that's described here, and then I'm accounting its orientation, and with help of vector u bar I'm gonna go there, and now this is L divided by 2 positive direction because the x coordinate axis is pointing that particular direction. All right, and now I'm constraining the motion along the global y direction. That means that this one here, this one have to be equal to 0. And that's going to give me the 5th constraint equation. Yes, sir. What about, what will be the value of this final constraint? So the question is, what is the value of the final constraint? Okay, so again, the question is like, what this equation have to be equal to? That's what you're asking.
I'm asking non-zero value.
Okay, so that's free to move up however it wants. So it's not constrained. So we're just constraining that one single row in that equation, nothing else. So it can do whatever it wants because no constraints. Happy? Good. Okay, so this is my list of constraints. So I have 5 constraints. So what I'm doing is that I'm just mechanically, and again, do this, practice this in prior to midterm exam, such that if you have a vector of constraints and you have vector of generalized coordinates, then you can more or less automatically create your Jacobian matrix. I'm not going to look at the details of the mathematics, but look at the dimension of the Jacobian matrix. It consists of 5 rows because of 5 constraints, 6 columns because of the 6 generalized coordinates. That's how it goes. So based on these dimensions, you can tell that the degrees of freedom of the system is 2. Yes, 1. 1. Checking if you listen to me at all. So it's 1. So it's 1 because 6 minus 5 is not 2, but 1. Okay? Clear? So that's it. That's end of the step number 2. And step number 3 is to create the vector of generalized forces. And now we have here gravity that is applying. So let me take a look. So we have a gravity that is applying to both bodies. And now the first gravity force is applying here in the center of the mass. Here's a second. And then there's one additional force vector that is pointing in a global x direction. And that too is located in a body reference coordinate system of body B. So those are the 3 forces that are applying in the system. What I should do? Well, first I'm defining where the force is applying by using the equation that we are very much familiar with. Once we have that kinematic definition, then we can differentiate that with respect to generalized coordinates, and that's going to give us that mapping matrix that converts the forces from global coordinates to generalized coordinates. That's what we have to do. Okay, so let's start it. So let's first define where the force is applying in a body A. So I'm going to travel here again using the equation that I'm very much familiar with. So I'm first going to the origin of the body reference coordinate system, then accounting its orientation, and then with help of the vector u bar, I'm going to travel the rest of the way. Rest of the way. I don't need to travel because I'm already there where the force is applying. So this vector will be equal to 0. And it simplifies because this component will disappear. So what is left is this one. And once I differentiate that with respect to my generalized coordinates, my mapping matrix reads as it is shown here. So then I'm going to take my force vector, and this force is now applying in a global coordinate system. So it consists of 2 components because of global coordinate system. Okay? So the components are 0 and mass multiplied by gravity constant minus direction. Clear? Okay, so it's gonna give me the vector of 3 components because of the 3 tennorized coordinates. All right, so then next, so the body B. So again, I'm gonna travel here, I'm gonna count the orientation of body reference coordinate system, and rest of the way I'm gonna travel with help of vector U bar, meaning I don't need to travel because force is applying in the origin of the body reference coordinate system. Okay, so this is how I can express my kinematics. So what is left is this one because this will be eliminated, and my mapping matrix is all the same that in the previous case because of these special circumstances. Okay, so here's my force that is applying in a global x direction, this one, and here's my force that is applying in a, well, minus direction, which is a gravity force. And my force in total look like this. And basically what I'm doing next is that I'm combining these 2 forces, I'm putting them in a vector that consists of 6 components. 6 components because of 6 tennorized coordinates. Make sense? Make sense, or none of this stuff makes any sense? Makes a little bit of sense. Makes a great deal of sense. No comment. Okay, let's take a look. Okay, quadratic velocity vector, we are not gonna touch that. Why? Because again, body reference coordinate system is located in the center of the mass, so we don't need to do it. Okay? And then step number 5. This is the most painful step. And I got the message from some of you are saying that this is really, really painful step. Yes, it is. This is, something that is a bit hard to do it. But again, it's just the mathematics. Very mechanical mathematics, nothing more than that. So don't be worried about that. Don't be scared about this. Okay, how it goes. So let's go one step at a time. So first thing we need to do in this final step is that, this, by the way, this is what we are aiming to. That this is what we wanted to compute. So first we have here Jacobian matrix like we computed in a previous case. That will be first multiplied by velocity of tennorized coordinates. Again, no thinking. Don't think about the numerical values. Don't think about anything at all. Just do it. Just take the Jacobian matrix, put here the velocity of tennorized coordinates, and do this mathematical operation. What is it you're going to get as a result of that? You're going to get the vector of 5 components. This is how it looks. So it's a 5 components again because of the 5 constraint equations. And now comes the most painful step. But this is where you need to put a little bit of attention to. Because then I'm going to differentiate these 5 equations with respect to my tennorized coordinates. That's what this very minor sub-index is actually referring to. It is a little hard to recognize that what it means is a lot of work, even though that is a tiny notation here in the lower right corner of that vector. So now this is important to differentiate with respect to position of tennorized coordinates. And that helps us a little bit, because if you look at what are the position level components, there is not such many there, because this is velocity, here is a theta, so this is position level. So this is pretty much the only thing that you need to differentiate in the first row, and so on and so forth. Got it? Now, how it's gonna be, when I do this differentiation, it's gonna look like this. So quite a bit of zeros here because, translational coordinates are not mentioned in the previous case. So that's why they disappear. So only thing that is left is this matrix, and again the matrix will be same as in the case of Jacobian matrix. And I'm going to multiply that with velocity with no thinking, absolutely no thinking. Finally, my equation of motion, when I'm combining everything together, look like shown here, but the details are not shown. But let me run this to you with help of MATLAB. So let's see if this is going to be again one of those memorable moments in your life, because what I'm going to do is that I already implemented all the equations to MATLAB, and now I'm going to go ahead and solve it. Ready to see it. Okay, so let's take a look. Here is my MATLAB, so I'm going to solve it. And let me see, where is my figure. There's quite a bit of windows open here. Here. Very unclear animation. Let me run this to you again. So let me first solve it. Okay, and let me put this on active here. Can you see how it's moving? Pretty awesome. What do you say? You saw it was like, doing like this. This is how it behaves. Yes. You happy? Why is that you're happy? Because this is not how it works in reality. Is that, if you think about it, if we're going back here, look at this. Is it possible that it's flying like that? Not possible. Not possible at all. Because, look what happened. I have here revolute joint. And what happened in animation, it was not fulfilled, but instead the system was flying around. It was moving upwards and it was moving left and right. That's not possible, that it behaves like that. What explains that? Well, of course you don't know that, but I'm still asking, like, what explains that? If you're able to answer this question, then I will give you some extra reward for sure. But I don't know what it is, but think about it. This is very, very difficult question. This is related to the fact how we converted the set of differential algebraic equations to be ordinary differential equations. And what I did in my numerical integration was that I intentionally allowed a lot of errors to take place. And because of the errors, the constraints are no longer fulfilled. So let me get back to my MATLAB code, fix the error tolerance, and then here's my MATLAB code. This is the one that is now available in Moodle database. So here's my integration tolerance. Let me make this a bit tighter, like that. And let me run the whole thing again. So it's here, it's already solved. And here's my animation. Yeah, it's it's a bit hard to follow, but happy, looking better. Is it looking better? Are you now happy? Well, you were happy last time too, so you're happy all the time, so it doesn't matter what I'm doing. So it's always like looking good. Okay, what is that we can learn from this?
What did you change?
I changed the error tolerance. I'm going to explain the whole story to you in a second. What is that we can learn from this? What is that you learn? Never trust professors. Number one. Never trust computers. What is it we can trust then? Our common sense. Trust your common sense. There is even, there is a serious medical condition that is called simulation disease. If you're going to get the simulation disease, it's almost like no hope. So you need to see the medical doctor and explain that I have this disease. Can you please give me, red bills and blue bills? That they may help you a little bit. But what is this medical condition called simulation disease? It is a disease where you trust whatever computer is giving to you. And it's possible that the simulation could be correct. It could be correct. And it could be close to reality. But it's never exactly the reality. And if there is a conflict between the reality and simulation, which one you should trust? Reality, of course. Reality, if it is not making sense, it is not making sense. Simple like that. So be very skeptical what comes out of the computer, because it may be the matter of implementation problem, or it may be the matter of misunderstanding something. Here it was a little bit of misunderstanding. So what exactly went wrong? I know that it's time to have a break, but I'm still going to explain what went wrong, and then you're going to have your break. Deal? Okay. So at least the front row is saying like, yes, can do. Okay. So let's go back to my PowerPoint presentation. Let's see. Okay. So constraint stabilization is related to that subject matter that I promised to explain you brief. You know, the whole story of the why things went wrong is related to this picture. Remember, initially I got the set of differential algebraic equations. And then what I did was that I converted that to be set of ordinary differential equations. And how that happened, so what was the trick to make that happen? But the trick is very important to understand, you know, to see what went wrong in the previous case. You know, I differentiate my constraints twice with respect to time here. Twice with respect to time. But my constraints mean, by the way, what this means, what is the physical interpretation of this? It means that constraints are fulfilled in acceleration level. Nothing else except acceleration level. And of course I wanted that to happen, but more important than that, I wanted them to be fulfilled in a position level. Because what happens in a simulation procedure is that you go down here to velocity level, and then you go down to position level. What is it you're doing in each step when you do that? You can introduce a tiny amount of errors. And it's possible that once you have more errors and they keep on accumulating, then the constraints are no longer fulfilled in position level. They're always fulfilled in acceleration level, but not necessarily any longer in position level. And that's where we have to introduce additional thing that is called constraint stabilization. It's a very fancy name, but it means that I have to correct my constraints. And I have to force them to fulfill my position constraints. That's what the constraint stabilization is about. And right after break, I'm going to spend 3 slides to explain what's the deal with that. 3 slides. Deal? Okay, and then look at that. Then comes this. Let me show this to you because I wanted you to come back. This is it. These are the matters that I'm expecting you to know. And look, each one of them will be rated. Like description of planar body. Oh my God, 5 stars. So that's something that you have to know whenever you get into exam. And we're going to discuss about this. And then, but you know, another example. Just the 2 stars. You can skip it. But we get back to this. So, how much you need? 10 minutes. 10 minutes. Okay. So let me close this.